Thank you. Thank you for coming back. It's going to be my last one. So I have been talking about hyperbolic space and hyperbolic group and the projections and how to. I sort of try to explain how to build a quasi-tree from that kind of setting. And I'm not sure if it was clear, but I started with an example with axis in its orbit in the hyperbolic plane or hyperbolic delta hyperbolic space. Then they satisfy, as long as the action is proper, they satisfy three properties: P0, namely projection is uniformly bounded. Then you can talk about the distance. Then P1. Oh, I should have. Yeah. So this is a summary, but I changed the subject. But let me just say a few words. So projections are uniformly bounded. So P1. Yeah. So at most one is large, dA UBC, dB AC, DC AB. So this has a name. It's called Boerstler inequality. Boerstler inequality. Okay. Due to Jason Boerstler, he noticed this kind of thing for in the setting of mapping class groups or subsurfaces, and P2 finitely many large projection. Okay. Then if you have this kind of some setting or just some setting, so that satisfies those three, then you have a quasi-tree. So that was what the last theorem was telling you. Okay, and but you may remember that in the first talk I was talking about the mapping class group, and the main theorem was that mapping class group acts on a finite product of quasi-trees so that it gives a embedding to the product which is a QI embedding. So the theorem was this. So mapping class group of the surface acts on a finite product of quasi-trees. All of them are quasi-trees, so that this embeds them by QI way. So that was a theorem. So using this kind of technology for mapping class group, I'm going to find we found quasi-trees. But to apply this kind of setting, I mean to our machinery, you have to find some setting where those three properties are satisfied. So in this last talk, I like to tell you how or where you find this kind of setting for mapping class groups. And I'm not going to prove this theorem, but I like to introduce you to some important objects to study mapping class group, which are called the curve complex and subsurface projections. So which is hopefully is going to be useful for you in case you are interested in topology. So that's the goal of this last talk. Okay. So suddenly I start the section. Curve complex. So it's totally disjoint. It's about some topology, surface topology, but toward proving this kind of things. So suppose SGP is a compact orientable surface of genus G with P boundary components. Okay, namely, I just draw one picture for you. So this is S32 because this is boundary. Those two are boundary and genus 3. Okay, so that we call it. Maybe this is possibly 0. It could be closed surface. Okay, and now what is a curve complex or curve graph? The curve graph of S is a graph where, so to define the graph, I specify, I tell you what the vertex set is and how when I join two vertices where vertices are homotopy classes of essential simple closed curves on S period, and we join alpha and beta if they don't intersect up to I don't know, after homotopy. Okay, so I say a few words. So homotopy class, okay, you know homotopy class. Essential here means so alpha, simple closed curve alpha is essential if it is not homotopic to a point or this boundary component. Okay, so yeah, for example, in this picture, if you have this alpha, then this is not essential because you can homotopy into a boundary, and of course, if you have this alpha, since it's bounding, a disk here, so it's not essential, but you can draw some essential curves like this one. This is essential, and this is also essential. All right, and when I join alpha and beta, if they are they don't intersect after homotopy. So that means I homotop alpha and beta independently. Okay, if you So, for example, this one, even whatever you do, they have to intersect. But so this one. This gamma and alpha are intersecting into 2 points, but you homotop gamma a little bit, and you can make it disjoint. So that means, so here's a little part of the curve complex. So beta, but they are disjoint. So you disjoint on the surface. So you join in the graph, and alpha beta. Not disjoint, so you don't join, but gamma beta disjoint, so you join. So something like this. Okay, it's a part of the graph. Okay. Right. And also I want to say the surface SGP is sporadic if and P is at most 4, or G is 1 and P is at most 1. Okay, so there are 7 cases, sporadic one. Okay, for those one, we don't use this definition to define the curve complex because, for example, genus 1 and no puncture, so it means this is a torus. But any two, whatever you do, any two different simple closed curves after homotopy are intersecting. So you can't join any of them. So it's going to be just disjoint set. So for the moment, because I like to use this definition, let's forget about those exceptional cases. Okay. And also, those exceptional cases, the one goal for you to understand is for you to understand the mapping class group, and the mapping class group is understood. So you really don't have to think about it for this moment. Okay. Then one thing is that the trivial observation is that so mapping class group of the surface acts on of S, so I write it CS, acts on this by automorphism. Okay, because vertex is mapped to a vertex, because the simple closed curve is mapped to a simple closed curve by a Homeo, and also disjointness is preserved, so therefore it preserves the graph structure. Okay, so that's first trivial observation. And now lemma. So in this case, I told you that the torus case, the graph is going to be just points, no edges. But first I like to see it as a geodesic space, so I like to prove that it's going to be a connected graph. Okay. So suppose assume S is not sporadic. Then for any alpha, beta, and curve graph, namely two simple closed curves, I should say now, sorry. So declare, so each edge has length 1. Okay, I don't change the length of the edge, is always 1. So if this graph is connected, you can talk about the distance. So there is a distance, but maybe for the moment it could be infinite, but there is a distance. And also here I should have said this one. So this is intersection number between A and B, namely this is a minimum of a number of points. Oops. Here, so this is up to by homotopy. Okay, so you move around alpha and beta, so that they intersect minimally. Okay, if you are familiar with, if there is another way to say this number. So if I put the hyperbolic metric on the surface, then each simple essential simple closed curve is represented by a closed geodesic. And then you can really talk about, if you after you represent each of them by a closed closed simple geodesic, in that case, you can just look at the intersection number, because they intersect minimally automatically. But anyway, okay. So you just, like this case, you move around. All right. So then any alpha beta distance in the curve complex, curve graph, beta is at most 2 times the intersection number plus 1. Okay, so this is a formula. So in particular, this is connected. Okay, so if you have two alpha and beta, so there is some number, intersection number, and distance is going to be bounded by a finite number. So it's connected. So let's prove it. Any questions? Okay. This is by induction on intersection number. Well, maybe A and B. Okay, anyway. No, alpha and beta. Yeah, I don't change. So if this is 0, then so they don't intersect, so you join, therefore distance is 1. Okay, so this is true. Okay, yeah. And also, well, I don't know, this is necessary, but if this is 1, maybe at least as a warm-up, let's do it. I didn't start the induction yet. Let's analyze what's going to happen to here, because it's a good warm-up. Then, so the picture is you have alpha, and they intersect only in one point. So like this is beta, so this is the intersection point. Okay. So I kind of put a metric on the surface, and so take a union and look at the neighborhood of the union, and take the boundary. Okay. So and we have seen this picture in the lecture by Oshika Sensei. So my claim is that. So my claim is essential. Okay, this is first of all simple, but it's going to be essential because otherwise. So either this bounds a disk, or like bounds a disk, or a boundary curve. Boundary curve. Okay, but if this bounds a disk, that means S is a torus, right? But then S is sporadic, so I said this is not. If it's a boundary curve, that means S is S11, namely torus minus a disk. Because this is a boundary disk, it means it's a torus minus a disk. It's also sporadic, so this doesn't happen. So this curve is essential. But now this is disjoint from alpha and also beta, because by the definition, therefore distance between alpha and beta is at most 2, right? Because you have alpha, you have a boundary of n, you have beta, and this is disjoint you join by an edge, and disjoint by an edge, so it's at most 2. Okay, so so this is also true. Okay, so in the case intersection number is 1, you are also fine. Now let's do the induction. Now induction. So by induction, I like to show. Let's show. What do I want to show? D alpha beta minus this one is 1. Okay, I move this, and I like to show this number is always at most 1. So now suppose intersection number is at least 2. Okay, then do code surgery to beta. Okay, by which I mean this. So my goal is same as this one. Given alpha and beta, I like to find another curve which is better in the sense that you can apply the induction hypothesis. So let's draw the picture here. So you have alpha, this is simple, and then you have beta. Maybe it's intersecting like this. It's simple, but it moves around. So this is say I don't know, beta. Okay, and those are intersection points. And I'm saying there are at least 2 points like this. Okay, so I just take 2 points here next to each other on alpha. Then I start moving off, say in this direction, on beta from here. Okay, and I move along beta. So beta is a simple closed curve. Eventually it has to come back to here, but of course before that you have to pass through this point because it's on beta, right? So before I reach here, I have to reach here, but there are 2 ways for you to reach. One is this direction, and the other is from the other direction. So there are 2 cases. And like this there. So there are 2 cases. I don't know, this is case 1 and this is case 2. All right. In this case, also this is an oriented surface. So now I like to produce something which is disjoint, or so it's not exactly on beta, but I like to start a little bit off from beta to the right. Then since it's an orientable surface, when you come back this way, you have to come back on the right too. Sorry, no. Yes. No. no. I have to come back. Which am I coming back? So it's opposite. No. I'm coming back on this side. Right? So it's oriented. So imagine the band. Band has to be like this. So okay. So here, if I start this way, then I come back this way. Okay. Because imagine the easiest picture like this. So okay, good. So I start traveling like this, and I come back like this. Of course, I'm hitting alpha, and now I close up this way. So this is I call beta 1. Okay, this is another simple closed curve, and also the other side. Okay, I get this like this. Okay, this is beta 2. Okay, so from beta I produce two curves, simple curves, beta 1, beta 2. So that I call surgery. So case 1. So beta 1 and beta 2. Okay, this is a simple closed curve. Now let's observe that intersection number of beta 1 and alpha C. So I lost at least those 2 points. So intersection number is like this. Okay? I lost those 2 points at least. Maybe I'm picking up those other points. But also intersection number of beta 2 is also -2. Okay? On the other hand, beta 1 is disjoint from beta. So beta 1, beta is disjoint from it. That means this is 1, or at most 1. Okay. Beta 2, well, 1. Okay, because they are disjoint. Okay. So, distance between alpha and beta 1 is now I use triangle inequality. The alpha beta plus the beta 1, that is the alpha beta plus 1, and also the alpha beta 2 is at most the alpha beta plus 1. Okay? Now this was my goal. So from beta I produce beta 1, beta 2 whose intersection number is smaller by 2, but distance goes up at most 1. So now look at the left hand side. So here I lost at least 2 and I gain at most 1. So left hand side goes down, right? So by induction this is so by induction I proved it. Okay? Is there any questions here?
So you let intact the other sides other than these 2 points.
Yeah.
While doing surgery.
Could you repeat?
While doing surgery, we do not touch the other sides other than these 2 points.
The other sides. The other sides. Good question. I didn't use it because I didn't use the other side, but I'm happy because I proved it.
Can we do surgery beta into 2 parts, maybe beta 1 and beta 2?
Which I did, yes.
Yeah, without touching the other side.
Touching the other side.
Not touching the other side.
Oh, sorry. This is touching the other side. Yeah, maybe beta 1 is, yeah, beta 1 is hitting like this. Is that what you're asking? Yes, yes, so sorry. So
also maybe it's worth making the remark that because you already put the minimal position,
yeah,
they are essential.
a good point. Yes. So very good. So his point is that maybe beta 1, beta 2, or beta and beta 2 don't exist in the curve complex because it has to be essential, right? So I'm using triangle inequality, but if beta 1, beta 2 don't exist in the curve complex, the argument is empty. So good. I have to make sure that at least, but look this carefully. So in fact, if one of beta 1 or beta 2 is essential, you are done. So if beta 1 or beta 2 is essential, then done. Okay? Because of the induction. But maybe not. Maybe both of them are not essential. What does it mean? It means that this beta 1 is bounding a disk or is a boundary curve. Okay? So, like actually, maybe this is like this. Okay? And also this is like this. So this, I try to indicate a disk or a boundary component. Now it's time for you to use the rest. Since alpha is a closed curve, now you can use, and also if this is true, this is really the whole beta. There is no other intersection because it's bounding a disk. So now you use the other direction. You do surgery in the other direction. You get beta 1 and beta 2 in the other direction. Now, if again both of them are not essential, what does it mean? It means you get a complete, you reconstruct your surface, which is going to be a sphere with at most 4 boundary components, which is sporadic. So let me just say, if both are not essential, use the opposite side, and then, well, you win. So you have to think a little bit, but you can ask questions. Is there any questions? Yes?
What is opposite side?
Opposite side is really
Just the start from the left. Right?
the red. So actually in this case, it's really, your alpha is really this, nothing else. So if those beta 1, beta 2 are bounding a disk or boundary curve, first of all I claim intersection points are only 2 points. Now use the other side. Yeah. Okay. Case 1 is done. How about case 2? Case 2, again I produce two things that you hit on and then come back in this way. Okay? And now this one I can't make this new curve beta 1 disjoint from alpha. But still it's a little bit better because I do this. Okay? And also beta 2, I do this. Beta 2. So this is no, this is again, this is no. Sorry. Yeah, this is beta 2. This is my surgery. So what happened in this case? Case 2. So I beta 1, alpha is I beta alpha minus 1, okay? Because, so there used to be 2 points here intersecting, but now at least for beta 1 I lost this point. So I still have this point here, I lost 1 point here, okay? So this is true. And also intersection number beta and beta 1, and this case, yeah, intersection number is in 1. So I use a lemma beta 1, sorry, beta 1 is 2. Oh yeah, so I needed it, so I prove it here. Okay, intersection number 1. This is 1, and I remind you that in this case also beta 1 is essential. Why? If it's not essential, so this is beta 1, and it's either bounding a disk or boundary curve. But imagine. Can you think of any curve beta which is intersecting beta 1 only one time? It's impossible, right? You have to come back. So from this, you immediately say beta 1 is essential. Okay. So now, okay, look at this. Intersection number. Sorry. Yeah, okay. Intersection number goes down at least by 1, but distance, sorry, from this distance of alpha beta 1 is at most distance alpha beta plus 2. Okay, distance goes up at most 2, therefore the left hand side doesn't goes up. So this is the end of the proof. Okay, so this is a kind of typical argument, and anyway, good. Now, next important thing is subsurface projection. Okay, by the way, any questions? All right. So I still started the GP, and now let, as before, you have this one. Let Y be a set of incompressible and proper subsurfaces. Well, maybe connected to be A in S. Okay. Proper means, in this case, proper means A is not S. Incompressible means, what is the best way? So each component of the boundary of A is essential in S. I guess this is the right way to say. So picture, you have say this is S here. So one example is like this one, and this is for example essential incompressible proper connected subsurface. And also, I don't know, and like this one is also incompressible proper subsurface. And I'll assume any A and B different. Again, okay. So again, I have to say homotopy classes of. Okay, so everything has a homotopy. So when I say two are different, then it means they are not homotopic to each other. Then it's assumed then for any A and B, boundary of A and boundary of B intersect. So this is the assumption. For example, here, if this is A and this is B, boundary is intersecting. So boundary of A is here. Boundary of B, there are 4 components. So when I say they intersect, namely, there is one component from the boundary of B, one component from boundary of A, that intersect. Okay, that's what I mean by that. Now, yes.
That case, the intersection is done in minimal way. So because if you assume if we allow homotopy, because we can always make intersections. So you have to find minimal intersections.
Yes. Thank you. Yeah. So yes. What? Must. Good. Thank you. Must intersect. Yeah. So. Okay. Yeah. Yes. Must intersect. Yeah. Now define for given any y and a in y disjoint pi y a is you take a boundary and restrict it to y, which is in now I'm tempted to say this one, curve complex, but so in this picture, sorry, if this is y, so this is a boundary of A, and restricted to, so this is bad, but so this is a boundary of A restricted to y, okay? But this is a curve complex, so this is not a curve, this is just an arc. So I have to do something. So one way is you make it curve and arc complex. So now this is a curve and arc graph of y. Namely, I just do the same thing. This is namely the vertex set. Vertex set is homotopy classes of essential simple closed curve on y and essential arcs on y, but so boundary of y. So okay, arc. So it starts from the one boundary component and end with maybe another boundary component. So essential means again same thing. It's not homotopic to the boundary. Okay. For example, this one is not essential because you can just homotope it into the boundary. So this is a definition. This is a curve and arc complex, but also because you have a curve complex of y and curve and arc complex of y, and this is a subset because you know this is only curves. and this is curve and arcs. This is subset. And of course, okay, join them if this joined, the same rule. So, for example, if this is joined in here, then it's joined in here. But actually the fact is they are, you can sort of think they are, so this is actually QI to each other. So it looks like you put here, you can put arcs. It looks like it's much bigger, and maybe it's really bigger in the sense of metric space, but it is not. It's just because, so for example, if you look at this arc, there is a way for you to produce curves from this arc as I did from this surgery. Okay? Namely, if you have an arc, you look at the union of arc and the boundary of y. So, like this one and this one, and again take neighborhood and look at the boundary. Okay. So, okay, you can forget about this one. So, what I'm saying is that, for example, here you get, I just write, I mean, this one, because it, and also this one. And you notice that this new curve, simple closed curve, is disjoint from the arc because it's a boundary. So distance 1. So my point is that whenever you have an arc, there is a curve nearby, next to each other. So that's why it's not bigger. And actually you can prove, this is the inverse map. This is the inclusion and the inverse map. And you can prove it's going to be QI to each other. Okay, so since when I talk about subsurface projection, namely I'm projecting curves into subsurfaces y here, I don't want to do surgery all the time. So in fact, I work with curve and arc complex, but I pretend I'm in the curve complex, only curves. So you have to make a choice. And okay. Anyway, so this is, I define it this way. So maybe it's really in the curve complex. Okay. Now I like to verify the actions. I'm heading to that. First of all, okay, pi y. Yeah, this one. Diameter of pi y a is at most 1 in c y, maybe secretary arc. Why? Because so boundary of y, boundary of a is mutually disjoint curves, and you intersect with y, still disjoint arcs. What arcs? So diameter is 1. Any point is joined. So this is trivial. Of course, if you do surgery and you really get the curves, maybe it's not exactly 1, but in the curve and arc complex it's really 1. So that's good. This is P0. P1. So now I define distance A and B is distance in the curve complex and boundary y and boundary B y. So namely this is, I just defined y, and this is pi b, sorry, no, y a and pi y b. Okay. as before in the previous setting. Right. So now claim P1 if dx y z is more than 10, then dy x z is at most 3, and dz xy is at most 3, and P2 any, okay, so this is any x, y, z in y. Any x and y in y, number of subsurfaces in y, so that dz xy is at least 4 is finite. Okay, I'm going to, okay, first of all, so this one I proved. Those two, I say, they hold. Okay. Namely, remember this is exactly the setting. Properties I needed to produce a quasi-tree, and so by the way, this is original Bostock inequality. Okay. So let me, yeah, okay. Let me prove it. So I think for each one I need only 10 minutes, but maybe I prove only, which one I prove? Second one. Yeah, for example, proof of P1. Actually, there is something I didn't understand, but anyway, let me do. So suppose dx yz is bigger than at least 10. Then I'd like to show this. Well, the other one is exactly the same, so let me just show this one. Then, first of all, so where was the important inequality? So remember, d alpha beta is at the most alpha beta plus 1. Okay, so this was the most important one. So since distance is okay, this is measuring the boundary of y and boundary z in the curve complex of x. And this is true in any curve complex. So if distance is large, it means that intersection number is large. So then, I don't know why this is 10, but I only need 3 intersection. So maybe something. Then boundary y and boundary z intersect at least in 3 points in x. Okay, it looks like at least 5 points. Anyway, so I just need 3 points. Maybe I only need like 7, but let me just use 10. 3 points. Okay. Then what is the picture? So this is x, so this everything is s. Okay. So let me say that y and z has a large projection in x. That means they have to intersect, say, 3 points. Now I write y, boundary of y. So I don't know, boundary of y look like this. Okay, but actually, so let me just write. So I don't know. I'm not really a topologist, so I don't know. So maybe topologist is gonna write some other nicer, I don't know. Yeah. Okay. So So this red part is, of course, it continues. It is y, and you see the boundary. But they're intersecting at least 3 points, so you have a boundary of y, and boundary of z is going at least 3 points, and look at the 3 points next to each other, then no, something is wrong. What's anyway, so it's intersecting. Okay, so at these 3 points. So my point is at least the only okay, good. So my point is that this is going to be a boundary of z. So, okay, in this picture, so boundary y and boundary z are intersecting in 4 points. My point is, so if they are intersecting at least 3 points, and I look at the consecutive 3 points, then at least, and then you have 2 intervals on boundary of z next to each other, but one interval has to be in y. Okay, it can't be both outside. So there is sigma here. Okay. Then exists a sigma my in y. Okay, but and x. Sorry. And x. I'm talking about the picture in x, but sigma is disjoint from boundary of x, because it's in x, the boundary of x here. So now here you go. Oops. Yes. Boundary. So therefore, if I look at this one, y, so I claim this is 1 plus 1 plus 1 at most 3 is 3. Why? Because here you have sigma, and here you really have this, but this is disjoint, so this is from disjointness. And this 1 plus 1 is because the diameter of this one is at most 1, and the diameter of this one is at most 1. So that's why 1 plus 1 plus 1 is at most 3. Okay? So in this way, this is dy xz is at most 3. So I proved this. Okay. Now I'm going over, but I finish in wrapping this in. So now again I finish by stating his thing. So this setting, it was what? So this is y. So distinct surfaces intersect. I don't know how okay, maybe I just. So by applying a theorem, actually this is one theorem, then we found so again I look at the all curve complex in y, again, I look at the disjoint union, and then exists gamma. So first of all, this is one claim, and moreover, if there exists a subgroup of the mapping class group, which acts on this one. Okay, remember this is a collection of subsurfaces. So possibly, for example, this is maybe the orbit of some subgroup of one subsurface. Okay, acts on Y, then H acts on X, and this phi is H equivariant. Okay, so you see the structure of the argument or theorem is exactly the same. So you have those three ones, and at the end you have this one, and also here, since this Cy. Oh, I forget to say exactly the very important thing. Theorem by Mirza-Minsky says all Cs is delta hyperbolic, and X is some delta hyperbolic. Okay, sorry. So this is delta hyperbolic. It's a big theorem by Mirza-Minsky. So it's normal aligned. If each one is aligned, you get a quasi-tree. But here you don't get a quasi-tree because each one embeds in here. But at least it's a hyperbolic space. Okay. So well, anyway, this last talk was not try to prove this kind of machinery to apply to this setting, but I just wanted to introduce you to the curve complex and some basic techniques and this kind of important property which may be useful or something else. Okay, thank you.